Have you ever wondered how chemists get their recipes just right? From life-saving medicines to the perfect can of soda, it all comes down to one absolutely crucial concept. Today, we're pulling back the curtain on the world of molarity.
It really all boils down to a pretty simple question. Just think about your morning coffee or tea for a second. What makes it sweet? Well, it's the amount of sugar you've dissolved in it, right? That simple idea of how much is the core concept we're going to explore today. It's called concentration.
And trust me, this is not just about coffee. Concentration is critical in, well, almost everything. It determines if a medicine is actually going to help you or if it's harmful. It dictates how strong a piece of steel is. It can even determine whether a planet's atmosphere can support life at all. Yeah, getting it right is a really big deal.
So here's our game plan. We'll start with the key players in any solution. Then we'll get right to the heart of it with molarity. We're even going to use the formula to figure out what's in a can of soda. And finally, we'll master the art of dilution. Let's jump in.
Okay, so before we can really talk about concentration, we need to get our vocabulary straight. What is a solution actually made of? Turns out there are two key players here, and knowing the difference is fundamental.
The easiest way to think about it is like this. The solute is what gets dissolved, and the solvent is what does the dissolving. In our coffee example, the sugar is the solute and the water is the solvent. Usually, you have a whole lot more solvent than you have solute.
And because water is, well, water, and it's so incredibly important to our planet, we have a special name for any solution where water is the solvent. We call it an aqueous solution. From the oceans to the inside of our own cells, we are surrounded by and made of aqueous solutions.
Okay, so we've got our terms down. But how do we go from saying a drink is kind of sweet or really sweet to a precise scientific measurement that any scientist in the world can understand? Well, this is where molarity steps onto the stage. It's the chemist's go-to recipe for concentration.
So, what in the world is molarity? It's really just a way of counting the number of solute particles in a solution. Now, since counting individual molecules would be, impossible, chemists use a handy unit called a mole. You can think of a mole like a chemist's dozen. It's just a way of grouping a gigantic number of particles. So molarity is simply the number of moles of a solute packed into 1 liter of solution. Moles per liter, that's the key.
And here's the beautiful formula that puts it all together. Molarity, which you represent with a capital M, is just the moles of solute divided by the liters of the solution. Super simple, right? This means if you know any two of these things, you can always figure out the third. It's an incredibly powerful little tool.
Theory is great and all, but let's see how this thing actually works in the real world. We're going to take a peek inside a can of soda and calculate its exact sugar concentration using our brand new formula.
All right, here's our problem. We've got a standard 355 milliliter soft drink. And through some lab magic, we know it contains exactly 0.133 moles of sucrose. That's just plain old table sugar. So, the big question is, what's the molarity?
Okay, let's walk through this. Step 1, we just pull out the numbers the problem gave us. We have moles of sugar and the volume of the soda. Now, step 2 is crucial, and it's a spot where people trip up all the time. Our formula needs the volume in liters, not milliliters. So we have to do a quick conversion. 355 milliliters becomes 0.355 liters. Once that's done, all we have to do is plug those two numbers into our formula and let the calculator do the work.
And there it is, 0.375 molar. So what does that actually mean? It means that for every single liter of this soft drink, there are 0.375 moles of sugar dissolved in it. See? We just put a precise scientific number on exactly how sweet that drink is. Pretty cool? So calculating concentration is one thing, but what about changing it? This brings us to dilution. This is a super common and really powerful technique for taking a very concentrated solution and making it less concentrated, on purpose.
At its heart, dilution is just adding more solvent to a solution to spread the solute out. I mean, you do this all the time. Think about a glass of iced tea on a hot day. As the ice melts, what's happening? It's adding more water, the solvent, and the tea starts to taste weaker. That's dilution, right there in your glass.
Now, here is the absolute most important key idea to understanding dilution. When you dilute something, you're adding more solvent, but the amount of solute, the actual stuff that was dissolved, doesn't change at all. All the sugar is still in your iced tea, it's just swimming in more water now. This simple fact is what makes the math for dilution work so elegantly.
And that key idea leads us directly to this fantastic little equation. C1V1 equals C2V2. The 1s are for your starting conditions, your initial concentration and volume. The 2s are for your final conditions, after you've diluted it. Since the amount of solute is the same before and after, the left side of this equation always has to equal the right side.
Let's put it to work. Imagine you're in a lab, and you have a big bottle of what's called a stock solution. It's very concentrated. You take 0.850 liters of this 5.00 molar solution, and you add enough water to bring the total volume up to 1.80 liters. What's the new, weaker concentration going to be?
So this is where we start. A solution with a concentration of 5 molar. That's our C1. That is some pretty concentrated stuff, the kind you wouldn't use directly, but would dilute down for your experiments.
We plug all our numbers into the dilution equation, solve for C2, our new concentration, and we get our answer, 2.36 molar. And that makes total sense, right? We added a bunch of water, more than doubling the volume, so it follows that the concentration should be cut by more than half. The math confirms what our intuition tells us.
All right, so let's wrap this all up. We started with the simple idea of concentration, just how much of something is in a mixture. We learned that chemists get precise with a unit called molarity, which is just moles per liter. We also saw how to make solutions weaker through dilution, always remembering that key rule. The amount of solute never changes. And now we have 2 awesome formulas in our back pocket to handle all of these calculations. We've gone from a simple question about a cup of coffee all the way to the precise calculations that happen in labs every single day, in chemistry, in medicine, and manufacturing. These formulas aren't just math on a page, they are tools for understanding and building the world around us. So, now that you know the chemist's secret recipe, what will you create?